Hello. So today I wanted to just record a particular application of CNNs or convolutional neural networks. Convolutional neural networks, as we know, mostly what I see in internet people sharing and most of the people working in computer vision applications. CNNs are typically looked up as networks which will give us classification results. So typically to find out whether there's a cat in a picture or not, whether there's a cat or dog. So the way what I have found is most students think is as if CNNs are particularly suitable, or even neural networks, but are particularly suitable only for classification problems. But it's not true, and one can actually do regression problems using neural networks and CNNs. So today I will give one simple example of uh, how one can really implement CNNs in a very powerful way to do a localization, to solve a localization problem. Uh, so I will try to do is I will try to create a circle inside the image at a random position and of a random radius. And we'll create thousands of such images. And because we are creating these images, we can create a particular x by y, that is 200 by 200 pixel image, and can create random locations, xy locations, where we'll center the circle and we will create a random radius. So in this way, we can create thousands of random circles at random locations inside the image. And this doesn't require us to actually gather data. And one can really simulate these circles and create a lot of data set, a very large data set, just within matter of a minute. And after getting the data set, what we'll do is we will use these images and we'll feed these to a CNN. And the CNN will not use sigmoid or will not use tanh type of functions, which are kind of thresholding functions, but we will use the ReLU activation function. Now, ReLU activation function, if one thinks about it, it has a continuous output. Like the ReLU function, if you see it, if you look at its x and y, it is x equal to y when x greater than 0, and x and y equal to 0 when x less than 0. So we'll use ReLU activation function and we'll try to model a neural network which will start with a 200 by 200 pixel image, and then we'll do a CNN to create, to reduce that image layer by layer in 3-4 layers, so that the final image will have only final convolutional operation in that series will give us a just three numbers, x, y, and radius. Okay, so let's look at that, and I'll just implement it using Google Colab, so that you can also reproduce it. I'll go through the code line by line, so those who are interested, they can follow along. So let's get started. So let me first do the required imports. First, we'll import the OpenCV library, the NumPy library, the MATLAB PyPlot, Matplotlib library, the random library, and the TQDM library is just for it helps us in creating loading bars, which help us if you are doing a lot of long data loading. Then it helps you to keep track that okay, the program is not dead, it is actually loading something. So this OpenCV function is OpenCV library is actually essential here, because this will help us to create those images and create random circles within those images. So let's execute this, and this will import the libraries. Libraries are imported. Now, just to show you what I mean, let me, just create, so we'll first declare image size, which will be 200 by 200. Then we will add we'll create a random integer between 5 and 50, which will be our radius. So our radius of the circle can be anywhere between 5 and 50 pixels. And then I will create C of X, Cx and Cy. These are my X and Y locations. These will be again random integers sampled between radius and image size minus radius. So the circle will always be sitting inside the image. So you are never going out of the image on both sides or on the boundaries. So it creates a random integer which can be between the radius value and the image size minus radius value, both X and Y. And after this, we create this a blank image which will have all white pixels. Okay, so that's why I have created once but multiplied 255 and created a shape which is image size by image size by 3. So it has it's a colored image that I'm trying to create. This is just for example for you, but after this what we'll do is we'll create black and white images. This is just for visualization. If you want, I can try doing it just a single channel. Let's see how it works out. So we'll use single channel, and let's create a new image, which is so a new image will create. But so you can create new image, or you can just do CV2 on the blank image itself at Cx and Cy. We create a circle of radius rad, and these are a couple of the parameters which so 0 is the color of the circle. So we'll be filling the image with zeros, filling the circle with zeros, and we have the whole image which is 255. So it will be like a black circle on a white background, and -1 means it is filled, like it is not just a circle but with a border, but it is filled inside with all these zeros. Then we'll show this plot. Let's see how it works out. Oh, there was a error. Okay, so this is not new image. We'll use the blank image itself, and let's plot it again. Oh, again wrong image size. Okay, so let me just give me a minute. Let me check this out. Okay, so this should not be image size by image size by 1. This should be image size by image size. Let's see if it works. Yeah, so here you can see. So we created a random circle at a random location of random radius. Okay, and this is showing as yellow, but actually this is a problem with the matplotlib, not problem. This is the way it displays. If you have only a single channel image, it's not RGB image, it's just a single channel image, which one channel 255. I can even remove this 255 and just make it once. Let's see what it shows. Again, you can see now it is still showing. So it has all the background pixels filled as 1, and the circle is filled with zeros. And any number of time I run it, you'll see the circle changes its position and its diameter. So this is clearly able to create random circles at random locations. Now let's get started to. Now let's write a code to create a training dataset. Now this training dataset. So let's name this function which will create this large training dataset as create training data. So I'm creating a function which will create this. Now say training data will be stored in a variable called training data, which will be returned at the end. And after that, the number of training sets which I want to create is 10,000. So I'm writing L equal to 10,000. So there will be number of training images which will be returned by this. Now I want to create a training X-train. X-train will be all these images in a single large array. So it will have a size of L. Okay. So it has a size of L, image size by image size by 1. So this will have L images of each image of size, image size by image size. Okay, so 200 by 200 by 10,000. So this will be kind of a volume of the training set. Each of these slice in this volume is one image with a circle at a random position and random diameter. Okay, so we're creating L such images, like 10,000 such images, and their corresponding corresponding location values and the diameter radius values will be stored in a array which will be 3 by L. So 3 elements like this and L elements like this. So that means it will have every image X, Y, and radius will be stored, and there will be 10,000 such training Y values which will be stored here in this. So these are just placeholders. We'll finally place images in these. We'll finally place images and their locations in this. So for this, let's create a for loop which will go one by one and create all these images. So I'm writing for I in range L, like 0 to L, 0 to L minus 1 or 2 line. And then I copy the above commands where I'm creating random cx, random radius, and random y, and then let's put these locations and the radius value in the training set y. Okay, because this is our target, these are our target values which will be which the CNN will try to find out. Okay, but these are something which are known to us when we're creating these images, but these will not be known to the CNN. Okay, they will be shown to it during the training time, but during the testing time we will not show these values to it, and it will try to predict these three numbers y, 0, y1, and y2. This will try to which basically contain radius, x, and y value of the circle. After this, let's create a blank image of image size by image size with 255, or maybe let's do just one in this case, and then fill this blank image with a circle positioned at cx, cy, and radius, which is unique for each iteration in this, and then we will create the blank image. In the blank image, we add this, and then whatever is the return value, although this is the blank image itself changes, but we will take this and we'll put this single image in this volume of Xtrain. Xtrain has all these 200 by 200 images, and there are 10,000 of these. So we are going to create one of these, each one of these images, and go on putting them one by one in all these 200 places, and each one will be unique image, okay, with a unique xy and radius position. May not be completely different, but they will be somewhat they are randomly generated. So after this, let's return this x and y as a dictionary value in the training data. So we'll return the training data, but sorry, the training data is not being used. So let's delete this training data stuff. It will create confusion. So we're returning xtrain and ytrain from this function, and as two dictionary values. So after this, we can enter. So this created this function. After this, let's create this training data set, and this training data set is being created now. It may take a minute to create all these 10,000 images, but it will create pretty fast. It's even faster than my computer. Like Google Colab is able to do this faster than my computer actually. So now training data has all these xtrain and ytrain values. So just to take a look at it, let's take one example from this. Let's take a look or take a peek inside the training data set. I'm copying the training, I'm plotting the training data set X-train value, the first one of this. So we have 10,000 this, and I'm just taking the first one of this, reshaping to 200 by 200, although it is already 1, 200, 200, 1, which is actually equal to 200 by 200. So just to plot it, I have to reshape it again into 200 by 200. And then let's plot this, and also let's show the corresponding white trend values for that particular image at one. And you see we have a circle here in this image, which is you have a circle in this image. Okay, what is this showing? This is showing that sorry, one thing which I forgot is that in the white trend values, what I'm saving is all these x and y values which are there, they are scaled by the image size. For example, if 0 to 200 are my 1 to 200 are my pixel locations, or 0 to 199 and 0 to 199 on x and y, then what I'm doing is I'm scaling these pixel locations uh, by the image size. So 0 to 200 becomes 0 to 1, and 0 to 200 on y-axis becomes 0 to 1. So that way it helps me to, because whenever we train a neural network, it's always a good idea to scale everything between 0 and 1. So that's why the image pixels are also between 0 and 1, and the white train values are also between 0 and 1. So I have basically made these white trend values between 0 and 1, but while actually creating this shape, this circle, I'm using c underscore x and c underscore y. I'm not, but while saving in white trend, I'm saving c underscore x divided by m image size. So I'm scaling and saving. Okay. So, but you can always come back to c underscore x by multiplying image size. That we can see here. Let's multiply this whole thing. Let's do image size. Image size is all capital, I think. Now here you can see created. So this is the first one. Not very. This is a small circle. So let's go to the second one. Second one in this 10,000 stack. Um, Now here you can see, yes, this is the big circle. It's centered at, it should be at about x equal to 100 or something. As you can see 96, and y equal to about 150 or something, right? And its radius is about 48. That means it should be about, you can see, starts from about 100 and goes up to 200 kind of thing. Okay, so you can see that this is saving the white train correctly for each extra image. Okay, so this way we have actually I have starting from 1 to up to 10,000 such images we have created just now. And let's now in the next step, let's try to create a model which will now take these extreme images, and will also provide these white train values. Okay, and this model basically does not know, we are not telling the model that there is a circle inside, and and the aim of the model is to find the center and the radius of the circle. This is not being explicitly told to the model. What we are just telling is these are the images, and these are the three numbers connected with this image. Now the model will try to figure out on its own that what the user needs to say to it is that there is a circle inside at a position xy with the radius r, and the model needs to return x, y, and r, which is absolutely amazing when you really think about it. So let's start off with the model design. So for this, we'll first import the TensorFlow libraries and the Keras libraries, which are essential for designing this model. And once those libraries are imported, let's create the model. Now the first layer would be the input layer. In the input layer, we will have the layer input size will be image size by image size by 1. The third dimension is basically not relevant in this. It's just that there are uh, there are multiple images, such images which can go through the first layer, but each image will have a size of 200 by 200. And so this will be the image input. And then so the model will start from after this, where we will, the first layer would be, we create a convolution 2D convolution layer with a 5 by 5 kernel, but three such kernels. So 5 by 5 um, kernels, and each kernel have a depth of 1, because the image itself is having only a single dimension image. Is not a it's not a three channel image, it's a single channel image. So each kernel will be um, 5 by 5 by 1, and there will be three such kernels which will be run over the image. And so and we'll use activation, ReLU activation, for this layer, and with a stride of 1 and padding, and we'll do zero padding such that the output image output is same size as that of the input. As we are using three convolutional operations, or three kernels of 5 by 5 by 1, so we expect the output to be after this stage, the output will go image size by image size by 3. Okay, because the padding is there. So there will be no loss in terms of x and y dimensions. There will be increase in the third dimension because we are using three convolution kernels. So after this, let's add few other layers. So we'll reduce the convolution layer size. We'll reduce the next layer size by using a max tool, which will simply half the image from image size by image size to image size by 2 by image size by 2. So that means it will become from 200 by 200, it will go to 100 by 100. So once we have that 100 by 100, let's go to the next step. We will, let's now create few other convolution layers. Now let's use a 10 by 10 kernel, but three such kernels. Again, use a max pooling layer to um, reduce the size. So now it became 50 by 50, and then again let's go 20, and then do again use a so what we are doing here is we are it's not a 5 by 5, it's a um, kernel size is 3 by 3, and there are 5 such filters. So the output of this first layer would be image size by image size by 5, and the next layer after the max pool, it will become 100 by 100 by 5, and after the next in this layer, in the third layer, it will become again 100 by 100 by 10, and after this it will become 50 by 50 by 10, and after this it will become 50 by 50 by, sorry, it will become 25 by 25, 25 by 25 by 10 after this, and after this will become 25 by 25 by 20, and after this I think it will become something like, yeah, 11 by 11 by 20, and then let me copy a few other things. I actually have this code in another window running, so I'm able to copy from there right away. So here, after we do this, and then output, we connect the final, we flatten the final layer. The final layer is, the model here is designed in such a way that they reduce finally to a 3 by 3 by 1 for each image. For each 200 by 200 input to this model, the output is a 3 by is a 1 by 1 by 3 vector. Okay, so it's basically you can think of three numbers. So that's why I can flatten the last layer to get just a single vector with three elements, and then I connect the input and output using the model function here. And let's summarize this model output, and you can see the model starts with a 200 by 200 image input. Then it goes, there are 5 layers, it converts to 5 layers first by using 3 by 3 kernels, 5 such 3 by 3 kernels. Then it goes max pool and gets 100 by 100 by 5. Then it goes convolutional layer, again gets 49 by 49. sorry, then after max pooling it gets 49 by 49 by 10. Then sorry, in this layer what I'm doing is I have increased the stride. I increased the stride to 2. Okay, sorry about that. So increasing the stride itself, when I made the stride 2, it automatically almost halves the image. So you can see in the next layer it became from 100 to 200 to 100, then 100 to 49, 49 to 24, 24 to 11 to 5, 5 to 1, and then finally 3. So I'm using both strides as well as max pooling layer, okay, to reduce the size of the final output. So there are no fully connected layers in this. This is just pure convolution to convolution layers connections with ReLU activations in between. So every layer is after the convolution there is a ReLU activation, except the max pool layers. And after the layer model is ready, now we are ready to compile this model. So because this is not a classification problem, this is a regression problem, because the xy and radius values are continuous numbers. Okay, they can be anywhere between 0 and 2, 1, and 0 and 1 and 0. So x, y, r can be anywhere between 0 and 1. So that means this is not a 0 and 1 decision boundary problem. This is not a classification problem. This is a regression problem. That's why the loss function will mean squared loss error function, mean squared error function as the loss function is the most suitable, is the suitable model. We should not be using the binary cross entropy in this. Otherwise, it will not be able to perform as per your requirement in this. So we are using the optimizer, which is Adam optimizer, and again metrics. We are using mean square errors, although you will see that uh, putting a metric output gives you some results, but the loss function is already giving you that result. So anyways, so let's compile this. So if this is compiled, now we can train this model. So let's train this model. So we are using the training data as the input, and training data X train as the input, and training data Y train as the output. And we will use or do it over 3 epochs, and verbose equal to 1. So let's look at the training. Now this training will take you a couple of minutes to complete. Now, because there are 3 iterations, I'm expecting this training will take you some time, maybe about 5-6 minutes. So while this thing is running here, I actually had run this already in another output, but yeah, I cannot show that to you. So let's wait. Okay, so the training is about to complete. Yes, the training completed, and let's now we could achieve a loss of less than 0.005. Okay, so let's test the performance of this model on the training data itself, okay, on which it trained. So let's take one example. We took the training data X train, the second image out of that, and we reshaped it to a format which will be acceptable in the model, which is you have to make it in a way that it was actually in image size by image size. So we'll make it 1 comma image size comma image size comma 1, so that it goes into the model, and then print that, and then we'll also print the training data y train data, okay, of the second. So the second image corresponding y train data. So let's see how close these two are. So, oh no, so let me print them one by one. So this is the first prediction. Let me multiply image size in front of it so that it scales to 255. Okay, so this is the, and then this is the prediction. This is the actual. This is the actual. That one's the prediction, and this one is the actual location and radius values. So you can see this was actual was is 96 and it predicted 89. The 152 y location and predicted 145. and actual radius was 48 and it told 45. Okay, and you can look at this image also. So if you want to print this image, you can, I think we can print this image using this function here. Let's try to print this second image uh, and then see if these are correct. Okay, the second image, you can see the location is, X location is about 89, sorry, 96, and Y location 152, and the radius is 48. Okay, now the real test of this algorithm would be that if I can create another random image which is not in the training set, and let's see what's the performance of this algorithm over that. Okay, so let's copy that of code uh, which we created above and just copy and paste it here. Okay, so we create again the image, um, create a random image with CX CY values, and let's see. So this one was the original way of. So let me save this. Okay, so here what I did is I created an image, I plotted that image. This image has X, CX and so CY value, or this image has CX and so CY values. So those values I plotted CX, CY and the radius, which was 139, 145 and 46. And then I passed on this new image and not the Y values. I didn't pass in the X, Y and radius value into the model. I just passed in the image and asked it to give me the three numbers associated with this image, and it returned 129, 120, 130, 127, 49. Okay, XY values are not great, but not bad, and the radius is also pretty close. So we can repeat this again with another random image, and again see it is able to do. Again, it is very off because it's a small image. I think completely screwed it up, but the radius is almost close. But the XY values are very off. Let's try this at another one. Okay, so here you can see it is doing it much better. So for very small images, it is a little bit screwing up. But overall, you can see for very large images, for example, 76 to 70, 111 to 105, and 48 to 57. Okay, so this I hope gave you the idea of how to use CNNs for CNNs for regression problems, and this is actually an example of object localization, a simple example of object localization in image. So if you have an object at a certain location in an image, so this is something where you are not taking any real images and don't have to bother about collecting a large number of images, and just create random images on your own and do a prediction of the localization of the image. This is a good example I felt to demonstrate the object localization using CNNs. Okay, so that's it for now. Hope you enjoyed. Thank you.